Hello dear students, this is Devang Shah from LG Institute of Engineering and Technology. So far we have been learning this particular subject which is called Basic Electrical Engineering, and the subject code is 3110005. So in our previous session we have discussed about the chapter number 1, which is called a DC circuits. So again in a DC circuits, in our last session we have discussed the basic components of electrical circuits like resistance, inductor and capacitor. We have also discussed about the Ohm's law, where we found that the relation of resistance, voltage and current together, and that relation, how they are going to affect on the performance or operation of a specific circuit, that we need to understand. Later on we also discuss about the once you are going to connect resistances are in series or parallel. With this respect you can also find a voltage divider rule and current divider rules. We exaggerate all those points in our today's session. So let's start with the Kirchhoff laws. So first we need to understand here components of the circuit design. So why we are learning all this particular subject, why we are learning all those topics, because design an electrical circuit for a desired output, right? For that three basic components we learned, which is a resistance, inductor, capacitor. Now we exaggerate the importance of resistance components a part of the circuit design, understand the terminology of circuit design, and we'll start with one of the part of the circuit is called nodes, another part is called the branch, and third itself a circuit, right? After that we are going to learn about Kirchhoff current law, that then we are going to discuss about Kirchhoff voltage law and example or generalization. So let's start first with what is the node, branch. Let's say we'll start with the branch first. What is a branch? See, branch is not a single wire. There is a incorporation of components inside the any wire. So one component or with connected with end to end, we consider as a branch. So in a circuit where you connect the component, that particular you can see in this diagram, there is a single branch where there is a one wire and two components are connected in series. So even you consider one component, that's the end to end point of this component. Once you connect this end-to-end point of component in a particular circuit, you define this terminology as a branch, right? So you can also add more components, and obviously this is a kind of series combination. Same way, if you add one component at one wire, if you add another component at another wire, if you add third component at a third wire, three terminology or these three wires is considered as a branch. So in this you can see there are three components are connected as individual wires, but those are connected at a single point, right? So you can consider all these three components at a three branches. Same way, next part is the node. Right. So what do you mean by the node? So ultimately, where all elements are connected, you consider this is called a node. Right. So a node, or you can also consider as a junction, where all these three components are connected. That's defined as a node. So ultimately, what do you mean by node? So at any point, three or more than three components or three or more than three wires are connected with the component, that terminology is defined as a node. So this is so important terminology. Why? Because many students are making a mistake that they give given the definition like two or more than two wires or components are connected at a single point, which is completely wrong, as three or more than three components or three or more than three wires are connected with component, that is referred as a node, right? Okay, now more circuit terminology we need to understand, because if there is a resistance, if there is the branch, if there is the node, you can see here this one of the circuit where point B, as of this I consider as one of the point in a circuit where I'm going to find the voltage drop across point number B with respect to ground. So whatever voltage drop you are going to get, that particular voltage drop is called the node voltage. So why this is very important? Because whenever you are going to take a circuit, and at any point if you want to find the voltage drop at that particular point or that particular branch, you can find all the voltage drop with respect to ground. So this is one of the terminology in circuit design. Next terminology is we define as a path. Now what do you mean by the path? So ultimately all this terminology depends on the movement of current. So here the role of current in a circuit design is very important. Why? Because in our first session we have discussed the voltage is worked as a force, current is always in a motion, right? And resistance is nothing but a path. So once the current flowing through any resistance, right, that is defined as a path. So once the current is flowing through any resistance, that would have a voltage drop, and that depends on the polarity of this particular current or the voltage drop. If the current is flowing from top to bottom and the voltage drop is from plus to minus, that is a actual voltage drop. We consider that voltage drop is a positive voltage drop, right? But in like this, if the current is flowing from top to bottom but the drop is from minus to plus, we consider as a negative voltage. So here that is no positive, there is no negative. Ultimately everything depends on the direction of current. If the current direction is opposite, see, the voltage drop would be the same but the polarity is different. Now we are going to use this branch concept and node concept to design circuit. So ultimately circuit is nothing but a closed loop, right? Now everything defined based on the movement of current. So you need to here understand current started its journey from positive terminal of the battery and coming to the negative terminal of the battery. That means here current itself finishes the closed path. Current itself come to the same node when where he has started. This terminology is defined as a closed loop or a mesh, or we can consider as a circuit. Now always remember, to operate any home appliances, current must be passed through the complete closed path or complete path, right? So from where the current start, again current should add at the same battery or same source, that considered as a circuit. Why this is very important? Because when the current is flowing through any devices or current is flowing through any resistance, that would have a voltage drop, and that particular voltage drop would drive or would run your further circuitry or your appliances, right? So here three important concepts we learned. One is called the branch, another one is called the node, and third one is must be a closed path. So once you connect all these three terminology, all these three words together, that become a circuit design, right? So great the circuit analysis, and based on this we found two most important laws, and those laws are found by one of the scientists named as a Kirchhoff. So those laws, it becomes the Kirchhoff laws. So there are two laws based on the Kirchhoff's theory. One is based on the voltage and another is based on the current. So let's first start to learn with the Kirchhoff current law. Now before that, let's start with some of the important exercise. How can you find, how can you identify branches, how can you identify nodes, right, and how can you identify the loops? So first start with, let's start with the nodes. So you can see this in the circuit. Can you find how many nodes are there? Yes, can you guess how many nodes are there? So most of the students making mistake, they are saying that there are three nodes, but ultimately there are two nodes, right? See, I already told you nodes, that means three or more than three wires are connected at a single point, right? So here you can see the first, this particular point where two components are connected at a one point. This is the one of the node where more components, at least three or more than three components are connected at one of the point. This is a second node where three or more than three components are connected. But you can consider the point number X here. You can see the point number X is not defined as a node. So ultimately, most of the students are making that there are three nodes. Ultimately, there are only two nodes, right? Okay. In our same circuitry, if we want to find how many branches are connected, so I already told you at one particular point, if there are more number of components are connected, or one component with the end-to-end terminology or with the end-to-end wire, it is defined as a number of branches. So you can see here how many branches. There are 5 branches you can consider. At one of the branch you have 5 branch, or you can also consider as a 4 branch. Why? Because one VS in series with the R1, this is one of the branch. Same way R2 is another branch. R3 which is connected at one particular wire, it is also a branch. And same way the VO, or this particular current source which is called IS, is also one of the branch, right? So you can here either consider as a 4 branch or 5 branch, depends on the number of components. So we can quickly see this. There are 5 branches in normal terminology. Once you use for analysis, there are 4 branch, right? Now same circuitry, here we look for number of loops. So once you start in this circuit, can you guess how many loops? There are 3 loops if you start from the point number A. So you can see there are 3 loops. Loop number 1, this is loop number 2, this is loop number 3, right? So there are 3 loops. Again, you can also individually define the loop, right? Yeah. Now here, most important law we define as a Kirchhoff current law, right? So in Kirchhoff current law is always applicable to a node. So node is very important terminology for us. Why? Because it's a part of the circuit, right? So we can now apply Kirchhoff current law to any circuit. So your first job is to identify the node, right? And Kirchhoff current law must be applicable to a node. That means if there is no node, there is no Kirchhoff current law, right? So what this law says, so you can see here, you can identify one of the node, and that particular node, if some currents are entering and some currents are leaving from this node. So here you need to define the sum of entering current. Here you define that sum of entering current is equal to sum of outgoing current. So ultimately, the algebraic sum of current must be equal to 0 at particular node. This is called a statement of Kirchhoff current law, right? So you can see in the circuit where 3 currents are leaving. Let's say I2, I3 and I4 are leaving, and I1 and I5, those are entering current. So ultimately the sum of entering current is equal to sum of outgoing current from the node. So the algebraic sum of current, like I1 with function of t. So always say like this: I1 minus I2 minus I3 minus I4 plus I5 is equal to 0. That you need to identify the node, and where your next job is to analyze how many currents are entering and how many currents are leaving. So sum of entering currents is equal to sum of outgoing current. So ultimately here you can consider, let's say this is one of the example, like 6 ampere current is coming, and there are 2 branches, one current is 2 ampere, then another must be a 4 ampere. So here the algebraic sum of current must be equal to 0 at particular node. So this is what the statement is then, and it is applicable for the nodal analysis. So that's a part of further circuit analysis. So let's define here one of the example based on Kirchhoff current law, where your first job is to identify nodes. So can you identify how many nodes here? Yes, this is node number 1, node number 2, node number 3, and node number 5. So total here you can find 1, 2, 3, 4 and 5. So total 5 nodes. So now for each particular node we have to write a Kirchhoff current law. So you can see the node number 1 where I1 current is entering and I2 and I3 currents are outgoing, right? So ultimately the algebraic sum of current at particular node must be equal to 0. That means the sum of entering current is equal to sum of outgoing current. So ultimately minus I1 plus I2 plus I3 is equal to 0, where I1 current is entering but rest of the 2 currents are outgoing. So the algebraic sum must be equal to 0. Same way you can further analyze and go for node number 2, 3, 4 and 5 likewise. So this is node number 2. You can write, you can see this particular equation where I4 current is incoming and rest of the 2 currents are outgoing. Same way this is node number 3. So you can see particular equation. Again you can apply the same concept for node number 3, same way for node number 4. You can see the equation same way for node number 5. You can see this particular equation, right? So this is how you can apply KCL and you can solve any particular example. Now of voltage law. So here Kirchhoff's applied based on the current. Now the here Kirchhoff apply its method based on the voltage. So ultimately this is applicable to a loop, or this is applicable to a closed path, right? Same way in KCL is applicable to node. Here KVL is applicable to a closed path. So you can see here one of the this is there are two closed loops is available in this particular circuit. So you can find here. So write the equation for a particular loop number one. Let's say, and you can define all the currents in a clockwise direction. So here V1 minus I1 into R1 minus R3, but the current is I1 minus I2, because through R3 there are two currents are flowing which are in opposite direction of each other. So ultimately Kirchhoff laws are nothing but based on the balance sheet, right? So ultimately balance sheet must be equal to 0. So if let's say I'm going to apply a 10 volt in a loop, so 10 volt must be dropped across each resistance, right? So at the end the sum of algebraic voltage drop and sum of product of current and resistance must be equal to 0. So you can find here the sigma V plus sigma I into R must be equal to 0 for particular closed path. So same you can apply for the loop number 2 as well. So this is called Kirchhoff voltage law. Now it is applicable for the loop and mesh analysis, right? So ultimately KCL is applicable to node and KVL is applicable to loop, right? Let's say one of the example based on a KVL here, one voltage source you are applying and there are three resistances are connected in series. So in each resistance there is a voltage drop. So ultimately here you can apply the equation like minus Vs plus VR1 plus VR2 plus VR3 is equal to 0. So ultimately once you are going to apply a 10 volt, let's say, so the voltage drop across R1 is let's say 2 volt, the voltage drop across R2 is let's say 3 volt, that then the voltage drop across R3 must be 5 volt. So ultimately the voltage drop across R1, R2 and R3 must be, that's the summation of voltage drop across R1, R2 and R3 must be equal to the applied voltage of Vs, right? So now this is applicable to individual loop. Again in this particular loop, can you write the equation of KVL? Just try it. So here your first job is to identify the loop. Same way in a KCL you have identified the nodes. Here you have to identify the loop. So this is a loop A, B, C, D, E and F. In this particular loop, if we apply the equation, that equation would be looking like this way, right? So ultimately the source, summation of source is equal to the summation of voltage drop across resistances. Now this is one of the numerical that based on the KVL and KCL. So you identify this particular circuitry where there are two loops, right, and there are two nodes ultimately. So your job is to find here the flowing current of I1, I2, and the third branch, that is the current which is passing through R3 is equal to I1 minus I2. So ultimately I1 is flowing in a one loop, right, which is passing through 10 ohm resistance, then I2 which is passing through 4 ohm resistance. So across 8 ohm resistance you can see the flow of current is I1 minus I2. So based on here you can find the nodes as well as you can find the loops. So here once you apply KVL and KCL, so let us say you apply the KVL in loop number 1. So once you apply the KVL in loop number 1, you can see this. Based on this terminology, you find a specific equation of loop number 1 where you apply a KVL. So once you apply the KVL in a loop number 1, so that would be the equation is 10 I1 plus 4 I2, that is equal to 20. Same way you apply the KVL in loop number 2, so you can find another set of equation which is called 8 I1 minus 12 I2 is equal to 12. Now this two particular equation you found, based on that your job is to find the values of I1 and I2. So you can straight away you can apply elimination method, which is a mathematics method, and from that you can be able to find I1 and I2. So ultimately once you find I1 and I2, you can also find the voltage drop across individual resistances, right? So let's say you will find here after this particular solution, you can find here the value of I1, that is equal to 1.895 ampere, and I2 that is equal to 0.263 ampere. So which is passing through 8 ohm resistance is nothing but I1 minus I2. So based on current values I1, I2 and I1 minus I2, you can be able to find the voltage drop across 10 ohm resistance, 4 ohm resistance, that is a particular bulb, and the 8 ohm resistance, right? Thank you dear students. here we have finished Kirchhoff law, right? So this is ultimately we are going ahead with the more understanding of the circuit fundamentals. Then we apply more theorems, more laws, and later on we have to solve a very big networks, right? Thank you very much.